So here's something you probably don't think about very often. And honestly, that's a good thing. Every single day, all around you, there are enormous quantities of chemicals being made, moved, stored, and used. Thousands of tons of ammonia, chlorine, ethylene, sulfuric acid, substances that if you encountered them in their raw form would be genuinely terrifying. They're flowing through pipelines under your city. They're sitting in tanks at facilities you drive past on the highway without a second glance. They're being loaded onto rail cars and barges and trucks that share the road with you. And the vast, vast majority of the time, nothing happens. The systems work. The valves hold. The operators follow the procedures, and everything stays exactly where it's supposed to stay. But sometimes it doesn't. And when chemistry goes wrong at an industrial scale, the consequences can be almost incomprehensible. We're talking about events that can reshape entire cities, change laws across nations, alter the course of how we think about industry itself. These aren't just accidents. They're stories. Deeply human stories about ambition and negligence, about what happens when economic pressure meets physical reality, about the gap between what engineers design and what actually gets built, maintained, and operated over years and decades. Tonight, we're going to walk through those stories together. Slowly. There's no rush. We'll start way back, further back than you might expect, and we'll work our way forward through time, watching how the chemical industry grew, how the disasters changed, and how, sometimes painfully, sometimes tragically late, people learned from what went wrong. And along the way, I think you'll start to see patterns. Because these events, separated by decades and oceans and completely different chemicals, often share the same quiet human roots. Let's start at the beginning, or at least as close to the beginning as makes sense. Because people have been working with dangerous substances for a very long time. Alchemists in the medieval period handled mercury and arsenic and all manner of volatile compounds, and plenty of them poisoned themselves in the process. Miners have known for centuries that certain underground atmospheres could kill you. They called it fire damp or choke damp, and they sent canaries down into the shafts because the birds would die before the men would. But the idea of a chemical disaster, an industrial-scale event where manufactured or stored chemicals suddenly escape and harm large numbers of people, that's really a product of the modern age. It required the existence of the modern chemical industry itself, and that industry, in the form we'd recognize it, really starts to take shape in the mid-1800s. The Industrial Revolution had been building for decades by then, but the chemical revolution that came alongside it was something else entirely. Suddenly, you had factories producing sulfuric acid in enormous quantities because you needed it for textile processing and fertilizer production and metalwork. You had the LeBlanc process churning out soda ash, which was essential for making glass and soap and paper, but which also produced hydrochloric acid gas as a byproduct. And for a long time, they just vented that into the air. Imagine living downwind of one of those plants. Your crops dying, your lungs burning, the paint peeling off your house. That was reality for communities near chemical works in northern England in the 1830s and 1840s. In fact, that's where one of the earliest pieces of environmental regulation comes from. The Alkali Act of 1863 in Britain, which was specifically passed because the hydrochloric acid emissions from LeBlanc process plants had become so devastating to the surrounding countryside that Parliament couldn't ignore it anymore. Think about that. The very first chemical regulation wasn't prompted by a single dramatic explosion. It was prompted by a slow, grinding, everyday poisoning of the land and the people who lived on it. And that's a theme we'll see again and again: the chronic versus the acute, the slow leak versus the sudden blast. Both are disasters, but they get very different kinds of attention. Now, as the 19th century rolled on, the scale of chemical production kept growing, and so did the potential for things to go catastrophically wrong all at once. And this is where we need to talk about one of the most important substances in the history of both chemistry and disaster, and that's nitroglycerin and its slightly more manageable descendant, dynamite. Nitroglycerin was first synthesized by an Italian chemist named Ascanio Sobrero in 1847, and Sobrero himself was terrified of what he'd created. He called it a dangerous substance, warned against its practical use, and reportedly felt genuine guilt about having brought it into the world, because nitroglycerin is extraordinarily unstable. It's a pale, oily liquid, and it can detonate from shock, from heat, from friction. Sometimes, it seemed, from almost nothing at all. And yet it was also incredibly powerful, far more powerful than black powder, which had been the standard explosive for centuries. So despite the danger, people wanted to use it, especially in mining, in tunneling, in construction, anywhere you needed to move a lot of rock in a hurry. The problem was that transporting and handling liquid nitroglycerin was essentially a death sentence waiting to happen. And the death sentences came. In the 1860s, there was a string of devastating nitroglycerin explosions around the world. One of the most significant happened in 1866 at a Wells Fargo office in San Francisco, where a crate of nitroglycerin that had been shipped as something else, mislabeled, mishandled, sitting in a warehouse, detonated and killed 15 people, destroying buildings in every direction. There were similar explosions in Panama, in Sydney, in New York. The stuff was being shipped by rail and by sea, and nobody had a reliable way to keep it from going off. This is where Alfred Nobel enters the story, and his story is one of those fascinating cases where personal tragedy drives innovation. Nobel's family was deeply involved in the nitroglycerin business. His father, Emmanuel, manufactured it. And in 1864, at the Nobel family's factory in Hellenborg, just outside Stockholm, a nitroglycerin explosion killed 5 people, including Alfred's younger brother, Emil. Emil was just 20 years old. Now, some people would have walked away from nitroglycerin entirely after that. Alfred Nobel didn't. Instead, he became obsessed with making it safer. Not safe. You can't really make nitroglycerin safe, but safer, manageable, predictable. And after years of experimentation, he found that if you mixed nitroglycerin with a particular kind of absorbent earth called kieselguhr, it's basically diatomaceous earth, the fossilized remains of tiny marine organisms. The resulting paste was far more stable than liquid nitroglycerin. You could mold it into sticks. You could drop it, ship it, handle it roughly, and it wouldn't detonate on its own. You needed a blasting cap to set it off. He patented this in 1867 and called it dynamite, from the Greek word dynamis, meaning power. And dynamite changed the world. It made modern mining possible at scales that would have been unimaginable before. It carved tunnels through the Alps. It blasted channels for canals. It reshaped the literal landscape of civilization. But here's the thing. Even dynamite, even this stabilized version, was still an explosive. And the factories that made it, and the magazines that stored it, and the mines that used it, were still sites of tremendous risk. Throughout the late 1800s and into the early 1900s, explosions at dynamite factories and ammunition works were distressingly common. They were, in a sense, the first recurring industrial chemical disasters of the modern era. But the real shift, the moment when chemical disasters became something fundamentally different, something capable of affecting not just a factory but an entire city, came with the enormous scaling up of chemical production during and after World War I. And this is where the story gets darker and more complicated, because the same war that drove the development of chemical weapons also drove the development of the modern chemical industry as we know it. Let's talk about that for a second. Before World War I, the global center of the chemical industry was Germany. It wasn't even close. German companies, firms like BASF, Bayer, Hoechst, dominated the world market in synthetic dyes, pharmaceuticals, and industrial chemicals. And the reason they dominated was partly scientific culture. Germany had the best university chemistry programs in the world, a tradition going back to Justus von Liebig in the 1840s. But it was also industrial ambition. These companies invested heavily in research and development. They scaled up production aggressively, and they were willing to push into new and dangerous territory. The most consequential example of this is the Haber-Bosch process, which I think might be the single most important chemical innovation in human history, and I don't say that lightly. Fritz Haber, a German chemist, figured out how to synthesize ammonia from nitrogen and hydrogen gas. That might not sound like much, but think about what it means. Nitrogen is everywhere. It makes up about 78% of the atmosphere, but in its gaseous form, it's almost completely inert. Plants can't use it. Animals can't use it. To be useful as fertilizer, nitrogen has to be fixed, combined with other elements into compounds like ammonia or nitrates. For most of human history, the main sources of fixed nitrogen were animal manure, guano, that's seabird droppings, which were mined on an industrial scale from islands off the coast of Peru, and Chilean saltpeter. The supply was finite, and by the early 1900s, agricultural scientists were warning that the world was heading toward a nitrogen crisis. There simply wouldn't be enough fertilizer to feed the growing population. Haber solved that problem, at least in principle, in 1909. He demonstrated that you could combine atmospheric nitrogen with hydrogen under extremely high pressure and temperature in the presence of a catalyst to produce ammonia. Carl Bosch, an engineer at BASF, then figured out how to scale this up to industrial production. And that was arguably the harder problem, because the pressures involved were extraordinary, hundreds of atmospheres, and the hydrogen would attack and embrittle ordinary steel. Bosch and his team had to essentially invent new metallurgy, new reactor designs, new ways of handling gases at pressures that no industrial process had ever attempted before. The first commercial Haber-Bosch plant opened at Oppau, Germany in 1913. And it worked. Synthetic ammonia flowed out, and from ammonia, you could make ammonium nitrate, which was both an incredibly effective fertilizer and, not coincidentally, a powerful explosive. When the war broke out in 1914, this mattered enormously because Germany was cut off from Chilean saltpeter by the British naval blockade. Without the Haber-Bosch process, Germany would have run out of explosives within months. Instead, the synthetic ammonia plants kept the German war machine supplied for 4 years. It's one of those strange, uncomfortable facts of history. The same process that would eventually feed billions of people was first scaled up to sustain a war that killed millions. And those plants, the Haber-Bosch facilities, the explosives factories, the munitions works that sprang up across Europe during the war, they were enormous. They were running at maximum capacity under wartime pressure, and they were handling vast quantities of dangerous materials. the conditions were, in hindsight, almost designed to produce catastrophe. Workers were undertrained, safety margins were thin, production quotas took priority over caution, and the materials themselves, ammonium nitrate, TNT, picric acid, nitroglycerin, were inherently, fundamentally dangerous. So it shouldn't surprise you that some of the worst industrial disasters of the early 20th century happened at exactly these kinds of facilities. And the one that really set the template, the one that showed the world what a modern chemical disaster could look like, happened not during the war itself, but just after it, at that very same Oppau plant where the Haber-Bosch process had first been commercialized. On September 21st, 1921, a massive explosion tore through a storage silo at the BASF facility in Oppau. The silo contained a mixture of ammonium sulfate and ammonium nitrate, about 4,500 tons of it. The blast killed over 500 people, injured nearly 2,000 more, and essentially erased the town of Oppau from the map. Buildings were flattened for miles around. The explosion was heard in Munich, over 300 kilometers away. It left a crater that was roughly 100 meters across and more than 10 meters deep. Just imagine that for a moment. A hole in the earth, the length of a football field, carved out in an instant by a single detonation. And the thing is, this wasn't some freak accident, some bolt of lightning striking a powder keg. The explosion happened because of a routine operation that had been performed thousands of times before without incident. Here's what was going on. The ammonium sulfate nitrate mixture in that silo had a tendency to cake together over time. It would solid it into a hard, rock-like mass, and you couldn't just scoop it out with a shovel. So the workers at Oppau had developed a standard procedure for breaking it up. They would drill holes into the caked material and set off small charges of dynamite. Just little blasting charges, enough to fracture the mass so it could be shoveled and processed. And they'd done this hundreds of times. Some accounts say thousands of times. It had always worked fine. The small charges would crack the cake, the workers would clear it out, and everyone would go home. But on that September morning in 1921, something went catastrophically wrong. The small charge didn't just fracture the material, it detonated the entire stockpile. 4,500 tons of fertilizer-grade chemical, all going off at once. Now, why did it work all those other times and fail this one time? That question haunted investigators, and the truth is, we still don't have a perfectly complete answer. But the best understanding is that the composition of the mixture had shifted. See, ammonium sulfate by itself is relatively stable. It's hard to detonate. Ammonium nitrate, on the other hand, is a different beast. Pure ammonium nitrate can be detonated under the right conditions, especially when it's confined and when the initiating charge is strong enough. The mixture at Oppau was supposed to be mostly ammonium sulfate, with a smaller proportion of ammonium nitrate. And at that ratio, the blend was considered safe enough to blast. But over time, the ratio may have changed. Some batches may have had a higher concentration of ammonium nitrate than the workers realized. The caking process itself may have altered the chemistry, concentrating the more dangerous component in certain pockets. And when the dynamite charge went off in a region that happened to be rich in ammonium nitrate, it triggered a detonation that propagated through the entire silo. Think about what that means in terms of safety culture. The procedure was considered safe because it had always been safe before. Nobody questioned it. Nobody tested whether the composition of the material was still within the safe range. Nobody asked, what if conditions have changed since the last time we did this? It's a pattern you'll see again and again in the history of chemical disasters. The normalization of deviance, where a risky practice becomes routine simply because it hasn't caused a problem yet. Every successful repetition reinforces the belief that the practice is safe until the one time it isn't. The Oppau explosion was, at the time, the largest industrial explosion in history. It shocked Germany, and it shocked the world. BASF rebuilt, of course. The chemical industry always rebuilds. But the disaster raised serious questions about how explosive materials were stored and handled. And yet, if you're waiting for the part where everyone learned their lesson, and ammonium nitrate never caused another catastrophe, well, you're going to be waiting a very long time. Because ammonium nitrate would go on to be involved in some of the most devastating explosions of the 20th and 21st centuries. We'll come back to it. It keeps showing up in this story, like a recurring character that nobody can quite get rid of. But let's move forward a bit, because the 1920s and 1930s brought a different kind of chemical danger into focus. Not explosions, but poisoning. Slow, invisible, insidious poisoning. And the story I want to tell you now involves one of the most tragic and infuriating episodes in American industrial history. It starts with radium. You've probably heard of the Radium Girls. Their story has been told many times, and for good reason, because it illustrates something essential about how chemical disasters unfold when the danger is chronic rather than acute. These were young women, many of them teenagers, who worked in watch dial factories in New Jersey, Connecticut, and Illinois during the 1910s and 1920s. Their job was to paint the dials of watches and instruments with luminous paint. Paint that contained radium, a radioactive element that glows in the dark. The work was delicate, requiring a fine brush tip, and the women were instructed to shape their brushes by licking them. Lip, dip, paint. Lip, dip, paint. Over and over all day long, putting radium directly into their mouths with every stroke. Now, the company, the United States Radium Corporation was the main one, knew that radium was dangerous. The scientists and managers who handled radium in the laboratory used lead screens, tongs, protective equipment. But the dial painters were told the paint was harmless. Some of them even painted their nails with it, their teeth, their faces, for fun, because it glowed. They were called the Ghost Girls because they'd leave work shimmering with radium dust, and their clothes would glow in the dark. The effects took time to appear. Radium is chemically similar to calcium, so when you ingest it, your body treats it like calcium and deposits it in your bones. And there it sits, irradiating the surrounding tissue from the inside. The women began developing mysterious symptoms. Their jaws would deteriorate and crumble, a condition that became known as radium jaw. Their bones would fracture spontaneously. They developed anemia, tumors, necrosis. Some of them literally had their jawbones disintegrate in their dentist's hands. And when they got sick and tried to seek compensation, the company denied any connection between the paint and their illnesses. They hired doctors to produce fraudulent reports. They suppressed evidence. They argued in court that the women's symptoms were caused by syphilis, a deliberate character assassination designed to discredit them. The legal battle that followed, particularly the case brought by 5 New Jersey dial painters in 1927, became a landmark in occupational health law. The women were visibly dying by the time their case went to trial. Grace Fryer, the lead plaintiff, had spent 2 years just trying to find a lawyer willing to take the case against a powerful corporation. The case was eventually settled, with each woman receiving a modest sum and coverage of medical expenses, but the real legacy was broader. The Radium Girls' fight helped establish the legal principle that companies could be held liable for the health effects of occupational exposure. It contributed to the development of occupational disease labor laws, and it forced a reckoning, slow, incomplete, but real, with the idea that employers had a responsibility to protect workers from toxic substances, even when the effects took years to manifest. I bring up the Radium Girls in a discussion of chemical disasters because their story illuminates the other half of the equation. We tend to think of disasters as sudden: explosions, fires, clouds of poison gas, and many of them are. But some of the worst chemical disasters in history are the slow ones, the ones that unfold over years or decades, where the poison accumulates quietly, in bodies, in soil, in groundwater, and the full scope of the damage only becomes clear long after the exposure has ended. The Radium Girls were among the first to make that invisible catastrophe visible, to put human faces on it, to drag it into a courtroom, and force people to look at it. And that tension between acute and chronic disaster, between the explosion and the slow poisoning, runs through this entire history. Sometimes they overlap. Sometimes the same facility produces both kinds of harm, and as the 20th century progressed and the chemical industry grew ever larger and more complex, both types of disaster grew in scale. So let's talk about what happened as the industry expanded through the 1930s and 1940s, because this is where the sheer volume of chemical production starts to become staggering. The Second World War, like the First, was an enormous accelerant for chemical manufacturing. The demand for explosives, synthetic rubber, aviation fuel, pharmaceuticals, and new materials drove a massive expansion of chemical plants across the United States, Britain, Germany, the Soviet Union, and Japan. New chemicals were being synthesized at a pace that outstripped anyone's ability to fully understand their properties or their dangers. And the wartime mentality, produce at all costs, worry about safety later, created conditions that were, once again, ripe for catastrophe. One of the chemicals that came into widespread production during this period was one you've almost certainly encountered, even if you don't know its name: phosgene. During World War I, phosgene had been used as a chemical weapon, responsible for the majority of gas-related deaths on the Western Front. It's a deceptively simple molecule: one carbon atom, one oxygen atom, two chlorine atoms, and it smells faintly of freshly cut hay, which is a terrible combination of properties for a lethal gas. By the Second World War, phosgene had found extensive peacetime industrial uses, particularly in the manufacture of plastics and pesticides. The same molecule that had killed thousands of soldiers in the trenches of France was now being produced in bulk at chemical plants in places like West Virginia and Texas, often in communities where residents had little idea what was being manufactured next door. But the wartime chemical disaster that really demands our attention, the one that stands as perhaps the most devastating industrial explosion before the nuclear age, happened not at a chemical plant at all, but at a harbor. On April 16, 1944, a cargo ship called the SS Fort Stikine caught fire and exploded in the docks of Bombay, in what was then British India. The ship was carrying a mixed cargo that included cotton bales, timber, oil drums, gold bars, and about 1,400 tons of explosives, including a large quantity of ammunition and, crucially, a shipment of Category A explosives. The fire started in one of the holds. The exact cause was never definitively established, and despite efforts to fight it, the blaze reached the explosives. The first explosion came at around 4 in the afternoon. It was enormous, sending a column of smoke and debris thousands of feet into the air. Fragments of the ship were hurled across the city. Burning cotton bales rained down on the surrounding docks and neighborhoods. And then, About 34 minutes later came the second explosion, even more powerful than the first. This one devastated the entire dock area and sent a shockwave across Bombay that shattered windows miles away. The blast was felt as far as Pune, roughly 150 kilometers distant. Around 800 people were killed, thousands were injured, and the fires that followed burned for nearly 2 weeks, destroying an enormous swath of the city's port infrastructure. Now, the Bombay explosion wasn't purely a chemical disaster in the way that Oppau was. It was a wartime logistics failure, a consequence of packing incompatible cargoes together under the pressures of a global conflict. But it belongs in this story because it demonstrates something crucial about chemical danger. Context matters as much as chemistry. The same materials that can be handled safely under controlled conditions become catastrophically dangerous when they're improperly stored, improperly combined, or subjected to conditions like fire that the storage arrangements weren't designed to withstand. The explosives on the Fort Stikine weren't defective. The ship wasn't sabotaged. The disaster happened because of decisions about loading, stowage, and firefighting that in retrospect were almost unbelievably reckless. Cotton bales next to explosives, oil drums in adjacent holds, a fire that was fought with water hoses when the only real option was to scuttle the ship. And here's what connects Bombay to Oppau, and to so many of the disasters we'll talk about going forward. The warnings were there. Dock workers had expressed concern about the mixed cargo. The fire was burning for hours before the explosion, and there were opportunities to evacuate the area or to take more drastic action. But the decision-making was slow, fragmented, hampered by bureaucracy, and by an unwillingness to accept the worst-case scenario until it was too late. That reluctance, that human tendency to believe that things will probably be fine, that the situation is under control, that the worst won't actually happen, is maybe the single most consistent thread in the history of chemical disasters. It shows up everywhere. It showed up at Oppau, where they kept blasting the ammonium nitrate because it had always been fine before. It showed up with the Radium Girls, where the company kept insisting the paint was safe because acknowledging the truth was too expensive and too inconvenient. And it would show up again, with devastating consequences in the decades that followed the war, as the chemical industry entered what you might call its golden age, a period of extraordinary growth, extraordinary innovation, and extraordinary risk. Because in the late 1940s and 1950s, something happened that changed the scale of chemical production forever. The petrochemical revolution took hold, and suddenly, the entire landscape of what was possible and what was dangerous shifted in ways that nobody fully appreciated at the time. See, before the war, most industrial chemistry was built around a handful of core processes. You had your ammonia synthesis, your sulfuric acid production, your chlor-alkali plants making chlorine and caustic soda. Important stuff, absolutely. But the range of chemicals being manufactured on a large scale was, compared to what came next, relatively limited. What the petrochemical revolution did was crack open this vast molecular toolbox. Engineers and chemists figured out how to take crude oil and natural gas, these complex mixtures of hydrocarbons, and break them apart, rearrange them, recombine them into an almost endless variety of new compounds. Ethylene, propylene, benzene, toluene, butadiene. These became the building blocks for plastics, synthetic rubber, pesticides, pharmaceuticals, detergents, solvents, adhesives, synthetic fibers. The sheer variety of chemicals in industrial use exploded, and the quantities were staggering. A single petrochemical complex in the 1950s might process more raw material in a month than an entire pre-war chemical works handled in a year. And here's the thing. This wasn't happening in some remote corner of the economy. This was the engine of post-war prosperity. Think about what life looked like in 1945 versus 1965. In those 20 years, you got nylon stockings and polyester suits and vinyl flooring and plastic toys and Tupperware and synthetic fertilizers that doubled crop yields and pesticides that kept food cheap and plentiful. All of that came from petrochemistry. The phrase, "better living through chemistry," that was a DuPont advertising slogan, and for a while, people genuinely believed it without a trace of irony. Chemistry was progress. Chemistry was the future. And the companies making these products, DuPont, Dow, BASF, ICI, Union Carbide, Monsanto, they were among the most powerful and admired corporations in the world. But here's what was happening beneath that shiny surface. The speed of innovation was outrunning the understanding of risk. New compounds were being synthesized, scaled up to industrial production, and shipped around the world before anyone had really studied what happened when they leaked, or burned, or reacted with water, or accumulated in human tissue over years. The toxicology was lagging behind the chemistry by decades, and the plants themselves were getting bigger, more complex, operating at higher temperatures and pressures, handling more volatile and reactive materials, often in facilities that had been designed for simpler, smaller-scale operations, and then expanded and modified and retrofitted until the original safety margins were stretched thin. This is the period when a particular type of disaster starts becoming more common. The process, safety failure. Not just a chemical that's toxic, not just a material that's explosive, but a complex industrial process involving multiple chemicals, high pressures, elevated temperatures, and interconnected systems where a failure in one part cascades through the whole thing. And to understand why these failures happen, you need to understand a little bit about how a chemical plant actually works. Picture a refinery or a petrochemical plant. What you see from the outside is this dense forest of pipes and towers and tanks and valves. It looks chaotic, but there's a logic to it. At its heart, a chemical plant is a system for controlling reactions. You're taking feedstock chemicals and converting them into products, and you're doing it under very specific conditions. A particular temperature, a particular pressure, a particular flow rate, a particular concentration. Every one of those parameters matters. If the temperature drifts too high, you might get a runaway reaction. If the pressure exceeds what the vessel was designed for, you get a rupture. If the wrong chemicals mix in the wrong place, you get an uncontrolled reaction that can release enormous amounts of energy or toxic gas or both. So the entire plant is essentially a machine for keeping everything within safe boundaries. Thermometers, pressure gauges, flow meters, relief valves, emergency shutdown systems, flare stacks to safely burn off excess gas, layers and layers of controls, each one designed to catch a problem before it becomes a catastrophe. The trouble is that these layers can erode. A pressure relief valve that's supposed to open at a certain threshold can corrode or get blocked. An alarm that's supposed to warn operators of abnormal conditions can malfunction, or, and this is more common than you'd think, operators can get so used to false alarms that they start ignoring them. Maintenance gets deferred because shutting down a unit for repairs is expensive and disrupts production. Procedures get modified informally, with workers developing shortcuts that seem to work fine until the one time they don't. This is what organizational theorists call the normalization of deviance, and it's worth sitting with that phrase for a moment because it explains so much of what goes wrong in industrial settings. The idea is simple but profound. When you do something that technically violates the rules or the design intent, and nothing bad happens, that deviation starts to feel normal. You do it again. Still, nothing bad happens. Pretty soon, the deviation isn't a deviation anymore. It's just how things are done. The original safety margin gets eaten away, bite by bite, and nobody notices because each individual bite is tiny. The system drifts toward failure, gradually, imperceptibly, until some triggering event, which might be quite minor in itself, pushes it past the tipping point. And this brings us to one of the most significant industrial disasters of the mid-20th century, one that shaped chemical safety regulation for decades afterward. On October 21st, 1966, in the small Welsh village of Aberfan, a coal tip, essentially a massive pile of mining waste, slid down a mountainside and engulfed a school and several houses. Now, strictly speaking, Aberfan was a mining disaster, not a chemical one. But I mention it because it's one of the clearest, most heartbreaking examples of normalized deviance in industrial history. The National Coal Board had been dumping waste on that hillside for years. The tip was built on top of natural springs. Water was saturating the base of the pile, turning it into something like quicksand. Residents had complained. Local officials had raised concerns. The coal board's own engineers had noted the water problem. And nothing was done. Because the tips had always been there, and they'd never collapsed before, and moving them would be expensive and disruptive. 144 people died that morning, 116 of them children. The inquiry that followed was devastating in its conclusions. The disaster was entirely preventable, and the responsibility lay squarely with the National Coal Board's institutional complacency. I bring up Aberfan because that same institutional pattern, warnings ignored, risks normalized, economic considerations overriding safety, runs through virtually every major chemical disaster of this era. And the one I really want to talk about now, the one that changed everything, happened 18 years later and half a world away. Bhopal, December 3rd, 1984. If there's a single event that defines the worst-case scenario for the chemical industry, this is it. And to understand Bhopal, you need to understand what methyl isocyanate is and why Union Carbide was making it in a densely populated city in central India. Methyl isocyanate, MIC, is an intermediate chemical. You don't buy it at a store. You don't encounter it in daily life. It's used in the manufacture of carbamate pesticides, specifically a product called Seven, which was Union Carbide's brand name for Carbaryl. Seven was a hugely successful insecticide, widely used in agriculture across the developing world, and MIC is a key ingredient in making it. The thing about MIC is that it's extraordinarily reactive and extraordinarily toxic. It's a small molecule, just 4 atoms of carbon, hydrogen, nitrogen, and oxygen arranged in a particular way, and it reacts violently with water. Even small amounts of moisture can trigger an exothermic reaction, meaning it generates heat, which accelerates further reaction, which generates more heat. It's also denser than air, so if it leaks, it doesn't rise and disperse. It flows along the ground like an invisible river, settling into low-lying areas, filling basements and ground floors. Union Carbide built a pesticide plant in Bhopal in 1969, and by the late 1970s, the plant was manufacturing MIC on site rather than importing it. They stored it in large underground tanks, 3 of them, each capable of holding about 60 tons of liquid MIC. Now, here's where the normalization of deviance comes in, because the Bhopal plant didn't fail all at once. It degraded slowly, over years. By 1984, the plant was losing money. Demand for 7 had dropped. Union Carbide was cutting costs. Maintenance crews were reduced. The refrigeration system that was supposed to keep the MIC storage tanks cool, because keeping MIC cold slows down any unwanted reactions, had been shut off months earlier to save on Freon costs. The flare tower, which was designed to burn off any MIC vapor that escaped, was out of service for repairs. The vent gas scrubber, a safety system designed to neutralize escaping gas with caustic soda, was undersized and hadn't been properly maintained. The water curtain system, meant to knock down any gas cloud with a spray of water, couldn't reach high enough to be effective. Safety system after safety system had been allowed to degrade or had been taken offline. Each decision, individually, probably seemed defensible. A cost saving here, a deferred repair there. Together, they stripped away every layer of protection. On the night of December 2nd, a worker was flushing pipes with water as part of routine maintenance. Water entered tank 610, which held somewhere around 40 tons of MIC. The reaction began. Water and MIC reacted exothermically, generating heat and carbon dioxide gas. The temperature inside the tank began to climb. The pressure began to rise. And one by one, the safety systems that should have contained the situation weren't there. The refrigeration was off. The flare tower was down. The scrubber was inadequate. The pressure relief valve eventually opened. It was designed to, that was its job. And a plume of MIC vapor began venting into the night air over a city of nearly 1 million people. What happened next is almost unbearable to describe, and I want to be careful here because this isn't a horror story, and these were real people. But the scale of it matters, because the scale is what drove the regulatory changes that followed. The gas cloud drifted over the densely packed neighborhoods surrounding the plant, settlements where tens of thousands of people lived in close quarters, many of them in ground floor or basement dwellings, exactly the kind of low-lying spaces where a gas heavier than air would concentrate. People woke up choking, unable to breathe, their eyes burning. Many ran, but they didn't know which direction to go, and running, breathing harder, only drew more gas into their lungs. MIC attacks the moist tissues of the eyes, throat, and lungs. It causes pulmonary edema. The lungs fill with fluid. The official death toll was initially reported as around 3,800, but subsequent investigations and ongoing health studies suggest the true number of deaths attributable to the gas release is far higher. Estimates range from 8,000 to 16,000, with hundreds of thousands more suffering chronic health effects that persist to this day. Respiratory disease, neurological damage, reproductive problems, birth defects in children born to exposed parents. And here's what makes Bhopal so important from an engineering and regulatory perspective. It wasn't a freak accident. It wasn't caused by some unforeseeable chain of events. Every single contributing factor was known. The dangers of MIC were well understood. The importance of the safety systems was well understood. The risks of storing large quantities of such a reactive chemical near a dense population were well understood. Union Carbide's own plant in Institute, West Virginia, which also manufactured MIC, had more robust safety systems and was located in a less densely populated area, though even that plant had a leak in 1985 that injured over 100 people. Bhopal happened because of decisions, economic decisions, management decisions, maintenance decisions, that systematically removed the barriers between a hazardous chemical and the people living next to it. The aftermath reshaped the global chemical industry. In the United States, Bhopal was the direct catalyst for the Emergency Planning and Community Right to Know Act of 1986, which, for the first time, required chemical facilities to report what hazardous substances they were storing and releasing. It led to the creation of the EPA's Risk Management Program, which required facilities handling dangerous chemicals to develop and submit detailed worst-case scenario analyses. In India, it led to new environmental legislation and, eventually, to the establishment of the National Disaster Management Authority. Internationally, it accelerated the development of the Seveso directives in Europe, named, incidentally, after another chemical disaster, one that happened in a small town in northern Italy in 1976, 8 years before Bhopal. And that disaster, the Seveso disaster, is worth understanding in its own right, because it introduced the world to one of the most feared chemicals ever synthesized, and because the European response to it became a model for how governments can actually learn from catastrophe, slowly, imperfectly, but genuinely. So let's go to Seveso. July 10th, 1976. A Saturday. The town sits about 15 miles north of Milan, in the Lombardy region. It's a quiet, prosperous area. Farms, small factories, the kind of place where people tend gardens and hang laundry outside. And sitting right there among the houses and the fields was a chemical plant called Eichmesa, owned by a Swiss company called Givaudan, which was itself a subsidiary of the pharmaceutical giant Hoffmann La Roche. The plant manufactured trichlorophenol, which is a chemical intermediate, meaning it's not the final product. It's a building block used to make other things, in this case, herbicides, and the antiseptic hexachlorophene. Now, here's the thing about trichlorophenol production. One of the known byproducts of the manufacturing process, if temperatures get too high, is a compound called 2,3,7,8-tetrachlorodibenzo-P-dioxin. You might know it simply as TCDD, or just dioxin. And dioxin is, by weight, one of the most toxic substances humans have ever encountered. We're talking about a chemical where harmful effects in laboratory animals show up at doses measured in parts per trillion. Not parts per million, not parts per billion, parts per trillion. To put that in perspective, imagine a swimming pool. A part per trillion would be like a single drop of ink in about 200 Olympic-sized swimming pools. That's the scale at which TCDD can cause biological damage. The manufacturers knew this. The chemistry was well established. Everyone in the industry understood that you had to control the reaction temperature very carefully during trichlorophenol production, because if the temperature climbed above about 158 degrees Celsius, you started getting significant dioxin formation. And on that Saturday in July, the plant was shutting down for the weekend. A batch of trichlorophenol was in a reactor vessel, and the heating was turned off as part of the normal shutdown procedure. But here's what went wrong. After the external heating stopped, an exothermic reaction, a reaction that generates its own heat, continued inside the vessel. The temperature kept climbing. Without adequate cooling or monitoring during the shutdown, nobody caught it. The pressure built. And eventually, a safety disc, a rupture disc designed to prevent catastrophic vessel failure, blew open, and a cloud of chemical vapor vented directly into the atmosphere. That cloud contained trichlorophenol, sodium hydroxide, and somewhere between 1 and several kilograms of pure TCDD dioxin. The wind carried it southeast over the town of Seveso and surrounding communities. It settled on rooftops, on gardens, on the laundry hanging outside, on the grass where children were playing. And for days, nobody told the residents what had happened. This is one of the most disturbing aspects of the Seveso disaster. The plant managers knew almost immediately that a release had occurred. They knew what chemicals were involved. But the full communication to local authorities and the public was agonizingly slow. It took nearly 2 weeks before the Italian government ordered evacuations. 2 weeks during which people were living, eating, breathing in an environment contaminated with one of the most potent toxins known to science. Children developed a skin condition called chlorachin, painful, disfiguring lesions that are one of the hallmark symptoms of dioxin exposure. Animals started dying. Rabbits, chickens, cats. Within days of the release, small animals in the most contaminated zone were simply dropping dead. Eventually, the authorities divided the affected area into zones based on contamination levels. Zone A, the most contaminated, was evacuated. About 700 people had to leave their homes. Zone B, a larger area with lower contamination, had restrictions placed on it. Altogether, tens of thousands of people were affected to varying degrees. And then came the long, painful process of cleanup. In Zone A, they literally scraped off the topsoil. They demolished buildings. They put contaminated soil and debris into enormous lined pits. The area was essentially treated as a hazardous waste site. Now here's where Seveso gets complicated, and in some ways, more hopeful than Bhopal. The immediate death toll was remarkably low. In fact, no one died directly from the dioxin exposure, at least not in the acute phase. Dioxin is insidious, precisely because its worst effects are chronic and long-term. Follow-up studies on the exposed population, some extending over decades, have found elevated rates of certain cancers, cardiovascular disease, diabetes, and reproductive effects. But because the Italian health authorities actually committed to long-term epidemiological monitoring, setting up registries, tracking exposed populations over years and decades, Seveso became one of the most important sources of data on the health effects of dioxin exposure in humans. Tragic as the event was, the scientific follow-up was rigorous in a way that Bhopal's, frankly, was not. And the regulatory response was genuinely transformative. The European community, this was before the European Union as we know it, passed the Seveso Directive in 1982, formerly known as Council Directive 82/501/EEC. And what this directive did was establish, for the first time in European law, a comprehensive framework for the prevention and control of major industrial accidents involving dangerous substances. It required companies to identify the hazards associated with their operations, to implement safety management systems, to prepare emergency plans, and to communicate risks to the public and to authorities. It required governments to ensure that land use planning took industrial hazard zones into account. So you couldn't just build houses right up against a chemical plant without anyone asking whether that was a good idea. The original directive was updated after Bhopal in 1996, becoming Seveso II, and then updated again in 2012 as Seveso III. Each revision expanded the list of covered substances, tightened requirements, and strengthened public access to information. And this is the thread that connects Seveso to Bhopal and to everything that came before. The slow, iterative, often painfully reactive process by which societies learn to regulate hazardous industries. A disaster happens. People die or are harmed. There's public outrage. Investigations reveal that the risks were known, that warnings were ignored, that economic pressures overrode safety considerations. New regulations are passed. And then, for a while, things get better. Until complacency sets in again, or until a new type of hazard emerges that the existing regulations don't cover, and the cycle starts over. But let's stay in the 1980s for a moment, because this decade was, in many ways, the crucible in which modern process safety was forged. We've talked about Bhopal in 1984. But just 4 years later, in 1988, something happened on a platform in the North Sea that would fundamentally change how the oil and gas industry thinks about safety. And it's a story that deserves real attention. Piper Alpha, July 6, 1988. An oil and gas production platform operated by Occidental Petroleum, sitting about 120 miles northeast of Aberdeen, Scotland, in the North Sea. At the time, Piper Alpha was one of the largest oil producers in the North Sea, handling about 10% of the UK's total oil and gas production. It was a massive structure, a steel platform standing in about 500 feet of water, with production modules, accommodation quarters for over 200 workers, and a complex web of pipelines connecting it to other platforms and to shore. On the evening of July 6th, a series of events began that would, within a few hours, destroy the entire platform and kill 167 of the 226 people on board. Only 59 survived. It remains the deadliest offshore oil disaster in history. And like Bhopal, like Seveso, like Oppau, the Piper Alpha disaster was not caused by a single dramatic failure. It was caused by a chain of smaller failures, each one individually manageable, that linked together into catastrophe. The investigation, led by Lord Cullen, produced one of the most thorough and influential disaster reports ever written. And it's worth walking through the sequence of events, because they illustrate process safety principles with devastating clarity. Here's what happened. During the day shift on July 6th, maintenance workers were performing routine work on one of two condensate injection pumps, Pump A. Condensate is basically a light liquid hydrocarbon that's separated out during gas processing. As part of the maintenance, a pressure safety valve was removed from the pump. The work wasn't finished by the end of the day shift, so the open pipe where the valve had been was fitted with a temporary metal plate, a blind flange. And the work permit was signed and placed in the control room, noting that Pump A was not available for use. Now, here's where the chain starts. That evening, Pump B, the backup, tripped. It shut down automatically, probably due to a mechanical issue. The night shift crew needed to get condensate flowing again, so they looked at whether Pump A could be restarted. And this is the critical moment. The night shift supervisor either didn't find the permit noting that Pump A was out of service or didn't fully understand its implications. The permit system on Piper Alpha was paper-based, and the handover between shifts was inadequate. The information about the removed safety valve didn't effectively transfer from the day crew to the night crew, so they started Pump A, and because the safety valve was missing, replaced only by that temporary blind flange, condensate gas began leaking from the opening. The gas found an ignition source. At approximately 10 p.m., an explosion ripped through the condensate processing module. It wasn't the biggest explosion you could imagine. It was enough to blow out the firewall between modules and to knock out the control room. But many people on the platform survived the initial blast. The problem was what happened next. The fire from the initial explosion impinged on the gas risers, the large pipes carrying gas from other platforms that were connected to Piper Alpha. These pipes were carrying gas at enormous pressure. And here's the decision that turned a serious fire into an unsurvivable inferno. The other platforms connected to Piper Alpha, Tartan, Claymore, and MCP-01, could see that Piper Alpha was on fire. Their operators could see the flames from miles away, but they kept pumping gas through the pipelines because they had no authority or clear protocol to shut down production without authorization from Piper Alpha's control room. And Piper Alpha's control room had been destroyed in the initial explosion, so gas kept flowing. And at approximately 10:20 p.m., about 20 minutes after the first explosion, the intense heat caused one of the major gas risers to rupture. The resulting fireball was catastrophic, a jet of burning gas producing temperatures that could melt steel. The platform became engulfed. The accommodation module, where many workers had gathered following emergency procedures that told them to go to their quarters and await rescue, was directly in the path of the fire. The structure began to collapse. Many of those who survived did so by ignoring the official emergency procedures. Instead of going to the accommodation block and waiting for helicopter evacuation, which was impossible because the helipad was consumed by fire, they made their way to the edge of the platform and jumped from heights of 100 feet or more into the dark, cold North Sea, with burning oil on the surface of the water. It was a terrifying choice, but it was the only one that offered any chance of survival. The Cullen Report, published in 1990, made 106 recommendations, and virtually all of them were accepted. It led to a complete overhaul of offshore safety regulation in the UK. The old prescriptive regulatory approach, which told operators exactly what equipment to install, what procedures to follow, was replaced with a goal-setting approach, where operators had to demonstrate through a formal safety case that they had identified all major hazards and had adequate measures to control them. The responsibility shifted. Instead of the regulator telling you what to do and checking boxes, you had to prove to the regulator that your platform was safe. And if you couldn't prove it, you couldn't operate. This was revolutionary. The safety case regime became a model adopted by regulators around the world, in Norway, in Australia, in parts of Asia. And it introduced a concept that's now central to process safety everywhere. The idea that safety is not a static condition, but an ongoing demonstration. You don't install safety systems once and forget about them. You continuously assess, test, maintain, and update. Because the moment you stop paying attention, the moment you let maintenance slide, or let permit systems get sloppy, or let economic pressure override engineering judgment, you're back on the path that leads to Oppau, to Bhopal, to Piper Alpha. And yet, even after Piper Alpha, even after all those reforms, the oil and gas industry would face another catastrophic failure, one that happened not in the harsh North Sea, but in the warm waters of the Gulf of Mexico, and one that would test whether the lessons of Piper Alpha had truly been learned. And the answer, when it came, was devastating. April 20th, 2010. The Deepwater Horizon was a semi-submersible drilling rig operating about 41 miles off the coast of Louisiana, in a stretch of the Gulf of Mexico known as the Mississippi Canyon. It was drilling an exploratory well called Macondo, owned by BP, at a depth that would have seemed like science fiction a generation earlier. The seafloor sat nearly 5,000 feet below the surface, and the well itself extended another 13,000 feet below that, pushing down through rock and sediment to reach a hydrocarbon reservoir more than 18,000 feet beneath the waves. Think about that number for a second. 18,000 feet. That's roughly 3.5 miles of pipe and rock and pressure, all managed from a platform floating on the ocean's surface. The engineering required to do this is genuinely extraordinary, and so are the forces involved. The Deepwater Horizon wasn't BP's rig. It was owned and operated by Transocean, the world's largest offshore drilling contractor. Halliburton was there too, providing cementing services, the critical process of pumping cement into the well to seal it and prevent hydrocarbons from migrating up the wellbore. On that particular day, the Macondo well was nearly complete. They were in the process of temporarily abandoning it, essentially capping it off so they could move the rig to another location and come back later with a production platform. Temporary abandonment is supposed to be a routine procedure. You set your cement plugs, you run your tests, you verify the well is sealed, and you move on. But nothing about April 20th was routine. Here's the thing about deep water drilling. The pressures involved are immense. Down at the reservoir, you've got hydrocarbons under enormous geological pressure, constantly trying to push their way up. The only thing keeping them down is the weight of the drilling mud, a specially formulated fluid that fills the wellbore and exerts hydrostatic pressure downward, counterbalancing the upward pressure from the formation. It's like holding a cork underwater with your hand. The moment you lift your hand, the cork shoots up. The drilling mud is your hand, and the cement job at the bottom of the well is supposed to be a permanent barrier, a plug that seals the hydrocarbons in place so you can eventually remove the mud and still have a secure well. On the Macondo well, the cement job failed. Halliburton had pumped cement to seal the bottom of the well, but the cement didn't set properly. There were warning signs. Halliburton's own engineers had run computer models suggesting that the cement design, which used nitrogen foam cement to reduce its density, was unstable. The number of centralizers used to keep the casing centered in the well bore was fewer than recommended, which meant the cement might not distribute evenly around the pipe. There were indications that the cement slurry might channel, leaving gaps, but the decision was made to proceed anyway. Now, even a failed cement job doesn't automatically cause a blowout. There are supposed to be multiple barriers, layers of defense, one behind the other, so that if one fails, the next one catches the problem. This is the Swiss cheese model that safety engineers talk about, where each barrier is a slice of cheese with holes in it, and a disaster happens only when all the holes line up. On the Macondo well, on that particular evening, every single hole lined up. After the cement was pumped, the crew ran a negative pressure test, a critical diagnostic procedure designed to check whether the cement and other barriers were holding. You essentially reduce the pressure in the wellbore and watch to see if anything flows back up from the formation. If the barriers are good, nothing moves. If they're compromised, you'll see pressure building where it shouldn't be, or fluid flowing when it should be static. The crew ran the test, and the results were ambiguous. There was unexpected pressure on the drill pipe. They discussed it, they debated it, and then they rationalized it away, attributing the anomalous pressure readings to something called the bladder effect, essentially arguing that a rubber seal in the test equipment was trapping pressure and creating a false reading. This is one of those moments that, in hindsight, makes you want to reach through time and grab someone by the shoulders. The negative pressure test was telling them the well was not sealed. The cement had failed. Hydrocarbons had a path upward. And the people on that rig, experienced professional drilling personnel, talked themselves out of believing what the data was telling them. Not because they were stupid, not because they didn't care, but because they were under schedule pressure, because the well was already weeks behind and millions of dollars over budget, because the rig cost BP roughly $1 million a day to lease, and because human beings have a remarkable capacity to see what they want to see when the alternative is unwelcome. So they accepted the test results and moved on to the next step. Displacing the heavy drilling mud from the riser, the large diameter pipe connecting the well bore to the rig on the surface, and replacing it with lighter seawater. Remember, the drilling mud is what's holding the hydrocarbons down. Replacing it with seawater removes that crucial barrier. You're only supposed to do this after you've confirmed that your cement barriers are solid. They hadn't confirmed that, but they did it anyway. And now the hydrocarbons began to move. Gas from the reservoir, under tremendous pressure, began migrating up through the failed cement, up through the well bore, into the riser. At first, the flow was subtle, but gas expands as it rises and the pressure around it decreases. That's basic physics, Boyle's law. The same reason a bubble gets bigger as it floats up from the bottom of a swimming pool. Except this wasn't a swimming pool. This was a column of fluid nearly a mile deep, and the gas was expanding exponentially as it climbed. By the time it reached the surface, it was a geyser. At approximately 9:49 p.m., mud and gas erupted through the drilling floor. The blowout preventer, a massive 75-ton stack of hydraulic rams and shear mechanisms sitting on the seafloor, specifically designed to cut through the drill pipe and seal the well in exactly this kind of emergency, failed to activate properly. Investigations later revealed multiple reasons: a dead battery in one of the control pods, a miswired solenoid valve, pipe that had buckled in a way that prevented the blind shear rams from cutting cleanly through it. The blowout preventer was the last line of defense, the ultimate fail-safe, and it didn't work. The gas hit the engine rooms. The rig's engines, which drew in outside air for combustion, ingested the hydrocarbon gas and began to overspeed, revving uncontrollably as the gas provided an unregulated fuel source. Then came the explosions. 2 massive blasts ripped through the platform. Fire engulfed the derrick. 11 men died. They were workers, roughnecks, tool pushers, mechanics, doing their jobs on what was supposed to be a routine night. 115 others survived, many by jumping from the rig into the dark ocean, just as those men on Piper Alpha had done 22 years earlier. The Deepwater Horizon burned for 36 hours before it sank. And then came the part that made this disaster different from almost any that had come before. The well, uncapped on the seafloor, continued to pour oil into the Gulf of Mexico for 87 days. Somewhere around 4 million barrels of crude oil, roughly 210 million gallons, flowed into the ocean before engineers finally managed to cap the well on July 15th. It was the largest accidental marine oil spill in history. And here's where the story connects back to everything we've been talking about. The investigation, conducted by multiple bodies, including a presidential commission, found that the Deepwater Horizon disaster was not caused by a single error or a single piece of failed equipment. It was caused by a cascade of decisions, each one individually defensible in some narrow sense, but collectively catastrophic. BP had cut costs on the well design. Halliburton had used a cement formulation that their own tests suggested was problematic. Transocean's crew had misinterpreted the negative pressure test. The blowout preventer had known maintenance issues that hadn't been addressed. And the regulatory body responsible for overseeing offshore drilling, the Minerals Management Service, had been so compromised by its dual mandate of promoting oil production and regulating safety that it was essentially toothless. Does this pattern sound familiar? It should. It's Bhopal. It's Piper Alpha. It's the same story told again, in a different ocean, with different technology, but with the same underlying dynamics. Economic pressure eroding safety margins, normalization of deviance, the gradual acceptance of abnormal conditions as normal. Regulatory capture, the process by which the agency supposed to be watching the industry becomes too close to it, too dependent on it, too sympathetic to its economic arguments. And the diffusion of responsibility across multiple organizations so that no single entity feels fully accountable for the overall safety of the system. The aftermath reshaped American offshore regulation. The Minerals Management Service was broken up into 3 separate agencies, specifically to separate the revenue collection function from the safety oversight function. New rules were imposed on blowout preventer testing, well design, and cementing procedures. BP paid over $65 billion in cleanup costs, fines, and settlements, the largest corporate settlement in U.S. history at the time. But here's what stays with me about Deepwater Horizon. What I think about when I consider the arc of this whole story we've been following. The safety case regime that came out of Piper Alpha, that revolutionary idea that operators had to proactively demonstrate safety rather than just follow prescriptive rules. That system was in place in the UK North Sea and in several other jurisdictions by 2010. But it was not in place in the U.S. Gulf of Mexico. American regulators had studied the Cullen Report. They knew about the safety case approach, and they had chosen not to adopt it, in part because of industry resistance, in part because the prescriptive approach was more familiar, and in part because of the political dynamics around oil production in the Gulf states. So when the Macondo well blew out, the regulatory framework governing it was essentially the old-style, checkbox-based system that Piper Alpha had already proven inadequate. The lesson had been available. It just hadn't been applied. And that brings us to something I want to spend some time on, because it might be the most important thread running through all of these disasters, more important than any single technical failure or any individual act of negligence. It's the question of how knowledge moves, or doesn't move, across borders, across industries, across time. Because the engineering community, broadly speaking, does learn from disasters. Reports get written, regulations get passed, standards get updated, but that knowledge is unevenly distributed. What's well understood in one country's chemical industry might be completely unknown in another's. What's standard practice in offshore drilling in Norway might be unheard of in the Gulf of Mexico. And what was painfully learned in 1984 in Bhopal can be forgotten, or never absorbed in the first place, by a facility operator in Texas in 2005. West Texas. No, actually, let me back up. I'm thinking of a different facility first. The one I want to start with is the BP refinery in Texas City, Texas, March 23, 2005. And yes, that's the same BP. 5 years before Deepwater Horizon, the same. Company presided over one of the deadliest industrial accidents in the United States in decades. And the lessons from that disaster were sitting right there, fully documented, fully investigated, when the Macondo well blew out. That's the part that should keep you up at night. Except, of course, we're trying to do the opposite here. So let's just let that thought settle in quietly and walk through what happened. The BP Texas City refinery was one of the largest in the country, sprawling across 1,200 acres along the Gulf Coast. It had been built in the 1930s by Amoco, then changed hands when BP merged with Amoco in 1998. And here's a pattern you'll recognize by now. When companies merge, the focus tends to land on financial integration, branding, executive restructuring. Maintenance budgets at aging facilities have a way of getting squeezed. The Texas City refinery was old. Some of its equipment dated back decades, and internal reports, BP's own internal reports, had flagged serious safety concerns at the site well before the explosion. A 2004 audit found that the refinery had extensive maintenance backlogs and a culture where cost-cutting had eroded safety margins. Workers had reported problems. Supervisors had noted them. And yet the refinery kept running, because refineries are enormously profitable when they're running, and enormously expensive when they're not. On that March morning, operators were restarting a unit called the raffinate splitter, which is part of the isomerization process. Basically, it separates different hydrocarbon components. During the startup, liquid hydrocarbons were pumped into a tall distillation tower, a column called a blowdown drum. Now, this tower had a vent stack, an old design, a relic from an earlier era, that vented directly to the atmosphere rather than to a closed system. That's important. Modern practice would route those vapors to a flare or a containment system. But this was old equipment, and the upgrade hadn't been made. During the startup, the tower was overfilled. Instruments that should have warned operators about the rising liquid level either malfunctioned or weren't being monitored closely enough. The liquid overflowed, shot up through the vent stack, and a geyser of flammable hydrocarbons erupted into the open air, forming a massive vapor cloud at ground level. Something ignited it. The exact ignition source was never definitively identified, though there were several possible candidates nearby, including a running diesel truck. The explosion killed 15 people and injured more than 170 others. And here's what makes this one sting in a particular way. Many of the people who died weren't even working on the unit that exploded. They were in temporary trailers, office trailers that had been placed far too close to the process units. The trailers were there because, well, they were convenient, and no one had enforced the safe sighting distances that should have kept occupied buildings away from high-hazard equipment. Those trailers were obliterated. People inside them never had a chance. The investigation, led by the U.S. Chemical Safety Board, the CSB, which by this point had become one of the most important investigative bodies in American industrial safety, found the same constellation of failures we've seen over and over. Cost-cutting on maintenance, aging infrastructure that hadn't been upgraded, a culture where process safety indicators were ignored while personal safety metrics, things like slip and fall rates, looked great on paper. BP could point to declining injury rates among workers and say safety was improving, while the underlying process safety risks were growing worse. It's a distinction that matters enormously. Personal safety is about whether an individual worker trips or gets a cut. Process safety is about whether the entire system can catastrophically fail. You can have excellent personal safety statistics and still be sitting on a ticking bomb. Texas City proved that. The CSB brought in an independent panel chaired by former Secretary of State James Baker to review BP's safety culture across all its U.S. operations. The Baker panel report, published in 2007, was scathing. It found that BP had not established effective process safety leadership, had not adequately assessed process safety risks, and had not effectively communicated its safety expectations across the organization. 3 years later, Deepwater Horizon happened. Same company, same fundamental cultural problems. The Baker panel's recommendations were on the shelf. So think about what that means for our thread about knowledge transfer. This isn't even knowledge failing to cross borders or industries. This is knowledge failing to move within a single corporation from one disaster to the next in a span of 5 years. The lessons were internal. They were documented by BP's own commissioned panel, and they still didn't penetrate deeply enough to prevent the next catastrophe. That's how stubborn these patterns are. Now let me take you to another incident that illustrates the knowledge transfer problem from a completely different angle. April 17th, 2013. West, Texas. And this time I do mean West, Texas, which is actually the name of the town. It's a small community of about 2,800 people north of Waco. The West Fertilizer Company stored and distributed ammonium nitrate fertilizer. And if that chemical name rings a bell from much earlier in our conversation, it should, because ammonium nitrate is the same substance that devastated Oppau, Germany, in 1921. Nearly a century of knowledge about the explosive potential of ammonium nitrate existed. It was one of the most thoroughly documented chemical hazards in the history of industrial chemistry. On that April evening, a fire broke out at the facility. First responders arrived, volunteer firefighters, because West is a small town. They were fighting the fire when the ammonium nitrate detonated. The explosion killed 15 people, 12 of them first responders. It injured more than 160. It damaged or destroyed more than 150 buildings, including a middle school and a nursing home that were located shockingly close to the facility. The blast, registered as a 2.1 magnitude earthquake on seismographs. And here's the thing that should take your breath away, quietly, lying there in the dark. The West Fertilizer Company was storing between 40 and 60 tons of ammonium nitrate. Under the Emergency Planning and Community Right to Know Act, EPCRA, the law that came directly out of Bhopal, the one we talked about earlier, facilities holding more than 400 pounds of certain hazardous chemicals were required to report their inventories to state and local emergency planning committees. West Fertilizer had last reported to the EPA in 2012 that it held a maximum of 54,000 pounds of ammonium nitrate. But the facility had not been inspected by OSHA in nearly 30 years. The state of Texas did not have a state fire marshal's office with jurisdiction to inspect such facilities. Zoning laws had allowed homes, schools, and a nursing home to be built within the blast radius. The regulatory framework that was supposed to prevent exactly this kind of catastrophe existed on paper, but had not been enforced in practice. And the ammonium nitrate itself, this is a substance whose dangers were demonstrated catastrophically at Oppau in 1921, at Texas City in 1947, when a ship loaded with the stuff detonated and killed nearly 600 people, at Toulouse, France, in 2001, when an explosion at a fertilizer factory killed 31. The knowledge base was enormous. The regulatory tools existed. EPCRA existed. OSHA existed. The EPA's risk management program existed. But in a small Texas town, none of those systems had been activated with enough force to prevent volunteer firefighters from walking into a building full of burning ammonium nitrate without understanding what they were facing. This is the mature phase of the story we've been tracing, and it's more unsettling in some ways than the early chapters. In the 19th century, in the early 20th century, you could at least say that people didn't know. The science wasn't there yet. The regulatory frameworks hadn't been invented. But by 2013, we knew. We had known for 100 years about ammonium nitrate. We had known for 30 years about the need for community right-to-know provisions. We had known for 25 years, since Piper Alpha, about the limitations of prescriptive, checkbox-based regulation. The knowledge existed. It just wasn't where it needed to be, when it needed to be there. And this brings us to something that I think represents a genuine evolution in how we think about chemical safety, a shift that's been happening gradually over the last couple of decades, but really accelerated after West. It's the idea that safety isn't just about what happens inside the fence line of a facility. It's about land use planning. It's about where you allow people to live and work relative to hazardous operations. The Seveso directives in Europe had already incorporated this. Article 12 of the Seveso II directive explicitly required member states to ensure that land use planning policies account for the need to maintain appropriate distances between hazardous establishments and residential areas, schools, hospitals. That was 1996. In the United States, there was no equivalent federal requirement. Zoning decisions were left to local authorities, and in many places, especially in states with a strong deregulatory philosophy, those decisions defaulted to whatever the market would bear. So you got nursing homes next to fertilizer plants. After West, President Obama issued Executive Order 13,650, directing federal agencies to improve chemical facility safety and security. It led to updates in how facilities reported their chemical inventories, better coordination between federal and state agencies, and some improvements in how first responders were informed about nearby hazards. But it didn't fundamentally solve the land use problem, because in the American system, zoning is a local prerogative, and the federal government has limited ability to dictate where buildings can and can't go relative to industrial sites. So you have this fascinating and somewhat frustrating situation where the technical knowledge about chemical hazards is genuinely excellent, better than it's ever been in human history. We understand reaction kinetics, thermal stability, vapor dispersion modeling, blast radius calculations. We can simulate what happens when a tank of chlorine ruptures, or when ammonium nitrate reaches its detonation threshold. The engineering science is mature, but the social, political, and institutional systems that are supposed to translate that knowledge into actual safety on the ground, those systems are still patchy, still inconsistent, still vulnerable to the same pressures of economics and politics and sheer human inattention that have been present since the very beginning of this story. And that tension between what we know and what we do with what we know is really at the heart of the most recent generation of chemical disasters. Take the explosion in Tianjin, China, on August 12, 2015. This one was enormous, almost incomprehensibly so. A container storage facility at the port of Tianjin, operated by a company called Ruihai International Logistics, was storing hazardous chemicals including sodium cyanide, potassium nitrate, and, again, ammonium nitrate. Roughly 800 tons of ammonium nitrate, along with other oxidizers and flammable materials, packed into a warehouse complex that was located far closer to residential buildings than Chinese regulations permitted. The minimum required distance was 1,000 meters. The nearest apartment buildings were about 600 meters away. Some residences were even closer. A fire started in the warehouse. The exact cause was traced to the spontaneous ignition of nitrocellulose that had dried out because it wasn't being kept properly wetted. Firefighters responded and began applying water. And this is where the chemistry becomes critical, because some of the materials in that warehouse reacted dangerously with water. The water may have accelerated the thermal decomposition of calcium carbide stored nearby, generating acetylene gas, which is extremely flammable. The fire intensified, and then the ammonium nitrate went. There were 2 massive explosions within 30 seconds of each other. The second one was equivalent to roughly 21 tons of TNT. It registered on seismographs as a 2.9 magnitude event. It left a crater 97 meters across and was visible from space. 173 people were killed, including 104 firefighters. That number deserves a moment. 104 of the 173 dead were the very people who rushed toward the fire to save others. Many of them were young, some barely out of training. And a significant number of them arrived at the scene without being told what chemicals were inside those warehouses. They didn't know they were walking into a situation where applying water could make things catastrophically worse. They were doing what firefighters do. They saw a fire, they fought it, and the information that might have saved their lives existed. It was on paper somewhere. It just didn't reach them in time. The aftermath was staggering. Over 700 people were injured. Thousands of nearby residents were displaced. Entire apartment complexes had their windows blown out, facades sheared off. Cars in a nearby parking lot, thousands of them, brand new vehicles waiting for distribution, were incinerated in neat rows, their charred shells visible in aerial photographs that circled the globe within hours. The environmental contamination was severe. Sodium cyanide had been scattered across a wide area, and cleanup crews had to neutralize it with hydrogen peroxide before it could leach into groundwater or wash into the Bohai Sea. Now here's what makes Tianjin so maddening and so familiar if you've been following this thread with me. The regulatory framework in China actually prohibited this kind of storage this close to residences. The rules existed. The distances were specified. The licensing requirements were on the books. But Ruihai International Logistics had obtained its operating permits through connections and corruption. Investigations after the explosion revealed that the company's safety evaluation had been conducted by a firm whose own qualifications were questionable, and that key officials had been bribed or had financial ties to Ruihai. The company's actual license to handle hazardous chemicals had lapsed and been improperly renewed. Inspectors who should have flagged the proximity to residential areas either didn't inspect or didn't act on what they found. It was a cascade of institutional failure that reads almost identically to the story of West Texas. Different country, different political system, different regulatory tradition, and yet the same fundamental breakdown. The knowledge was there. The rules were there. The enforcement wasn't. In the aftermath, the Chinese government prosecuted dozens of people, including Ruihai's executives, port officials, and regulators who had signed off on permits they shouldn't have approved. Sentences ranged up to death with reprieve, which in the Chinese legal system typically means life imprisonment. The government also launched a nationwide inspection campaign of hazardous chemical storage facilities, and that's a pattern we've seen over and over. The disaster happens, the prosecutions follow, the inspections surge, the regulations tighten. The question is always whether the tightening holds, or whether it slowly relaxes as memory fades and economic pressures reassert themselves. But let's stay with this idea of information flow for a moment, because it connects to something broader that's been shaping chemical safety in the 21st century. One of the most important shifts in recent decades isn't a new regulation or a new technology, it's transparency. The idea that communities have a right to know what chemicals are being stored, processed, and transported near them. We talked about EPCRA, the Emergency Planning and Community Right to Know Act, which came out of Bhopal. That was 1986, and it was genuinely revolutionary in its time. The toxics release inventory it created meant that for the first time, anyone could look up what a facility in their neighborhood was emitting. But right to know is only as useful as the systems that deliver the information to the people who need it, when they need it. Think about those firefighters in Tianjin. Think about the first responders in West Texas. In both cases, the people running toward the danger didn't have a clear picture of what they were running into. And this isn't just a problem in China or small-town Texas. It's a systemic challenge everywhere. Hazardous materials databases exist, but they're often incomplete, outdated, or siloed in agencies that don't communicate well with local fire departments. The information might be in a filing cabinet at a state environmental agency, or in a federal database that a volunteer fire chief in a rural county has never been trained to access. The gap between information existing and information being actionable, that gap kills people. And this brings us to something that's been quietly transforming chemical safety in ways that don't make headlines but matter enormously. The digitization and real-time sharing of chemical hazard data. After Tianjin, after West, After a series of incidents that all shared this common thread of information failure, there's been a global push to create systems where first responders can access real-time inventories of what's stored at a facility before they arrive on scene. Some of these are apps. Literally, a firefighter pulls up a tablet and can see what chemicals are in which building, what they react with, what the recommended suppression approach is. It sounds simple. It sounds like something that should have existed decades ago. But building those systems requires cooperation between private companies who may consider their chemical inventories proprietary, regulatory agencies at multiple levels of government, and emergency response teams with wildly varying levels of technical sophistication. It's a coordination problem as much as a technology problem. And here's the thing. Even when the data systems work perfectly, they only help if someone checks them. If the fire is already raging and the first engine company is on scene within minutes, the pressure to act immediately, to start putting water on the fire, is immense. Training has to override instinct. Protocols have to be drilled so deeply that they become automatic. And that's a human factors challenge, which is really its own entire field of study. So let me shift gears slightly and talk about a disaster that illustrates a different dimension of modern chemical risk, one that's less about storage and more about transportation. Because we move staggering quantities of hazardous chemicals every single day, by rail, by truck, by pipeline, by ship. And every mile of transit is a mile where something can go wrong. On February 3rd, 2023, a Norfolk Southern freight train derailed in East Palestine, Ohio, a small town, about 4,700 people, right near the Pennsylvania border. The train was carrying a mix of cargo, including 20 cars loaded with hazardous materials, vinyl chloride, butyl acrylate, ethyl hexyl acrylate, ethylene glycol monobutyl ether, and isobutylene. The derailment was caused by an overheated wheel bearing on one of the cars. The axle had been getting progressively hotter, and wayside heat detectors along the track had actually flagged the rising temperature. But by the time the crew received the alert and initiated braking, the bearing had already failed catastrophically. 38 cars derailed. Some of them piled up and caught fire. Now, here's where the decision-making gets complicated and controversial. Several of the tank cars containing vinyl chloride were at risk of what's called a bleave, a boiling liquid expanding vapor explosion. Vinyl chloride is a gas at room temperature, but was being transported as a pressurized liquid. If the fire heated those tank cars enough to weaken the steel, while the pressure inside kept rising, they could rupture explosively, sending shrapnel and a massive fireball across a wide area. The potential blast radius was significant. So Norfolk Southern, in consultation with the governor's office and emergency management officials, made the decision to conduct a controlled release and burn of the vinyl chloride. They deliberately vented the chemical from 5 tank cars into a trench and ignited it. The burn sent a towering plume of black smoke into the sky. You might have seen the images. They were everywhere. When vinyl chloride burns, it can produce hydrogen chloride gas and phosgene, both of which are toxic. Phosgene, notably, was used as a chemical weapon in World War I. Residents within a mile were evacuated before the burn, and officials said air monitoring afterward showed levels had returned to safe thresholds. But the community was terrified, and understandably so. People reported headaches, nausea, burning eyes. Fish died in nearby streams, about 3,500 fish across 7.5 miles of waterway, and the long-term health concerns were enormous. Because vinyl chloride is a known human carcinogen. It's specifically linked to a rare form of liver cancer called hepatic angiosarcoma. The anger in East Palestine was palpable, and it cut in every direction, at Norfolk Southern for operating the train, at regulators for not requiring better safety standards on rail cars carrying hazardous materials, at the EPA for its initial response, at state officials for the evacuation decisions. And underlying all of it was a question that's been simmering in chemical safety for years. Who bears the risk of transporting hazardous materials through communities that have no say in the matter? The people of East Palestine didn't choose to live next to a chemical plant. They lived next to a railroad, which is true of thousands of American towns. And on any given day, trains carrying chemicals far more dangerous than anything stored in a typical factory roll through those towns, sometimes in the middle of the night, sometimes with outdated tank car designs that everyone in the industry knows are vulnerable to puncture and fire. After East Palestine, there was a bipartisan push in Congress for the Railway Safety Act, which proposed requirements for upgraded tank cars, more wayside detectors, larger train crews, and stricter reporting requirements. As of now, the legislation has moved slowly. The rail industry is powerful, and the lobbying is intense. Some provisions have been implemented through executive action or voluntary industry commitments, but the comprehensive bill has stalled. And that pattern, urgent public demand for reform, followed by gradual dilution as the news cycle moves on and industry pushback intensifies, that's not new. We've seen it after almost every disaster in this story. But East Palestine also highlighted something genuinely new about chemical disasters in the 21st century, and that's the role of social media and real-time information sharing. Within hours of the derailment, residents were posting videos, air quality readings, water test results. Independent journalists and environmental activists were on the ground before some federal agencies had fully mobilized. The information ecosystem around the disaster was radically different from anything that existed during Bhopal or even Deepwater Horizon. And that cuts both ways. It meant the community had access to information faster than ever before, but it also meant misinformation spread rapidly. Claims circulated that the contamination was far worse than official readings indicated, or that the government was covering up the true extent of the damage. Some of those claims may have had merit, some were exaggerated. Sorting signal from noise in real time during an active environmental emergency is genuinely hard. And this tension between transparency and trust is something that's going to define chemical safety going forward. Because the public's trust in both corporations and regulatory agencies has eroded significantly over the past few decades, and not without reason. When people in East Palestine were told the water was safe to drink, many of them didn't believe it. And you can understand why, given the history of communities being told everything was fine when it wasn't. Flint, Michigan, and its lead-contaminated water supply loomed large in the public imagination. The legacy of Love Canal, of Woburn, of every time a company or an agency said, the levels are within acceptable limits, while people got sick. That legacy makes trust incredibly difficult to rebuild. So where does that leave us? We're in a moment where the technical knowledge to prevent most chemical disasters genuinely exists. The chemistry is understood. The engineering controls are available. The risk assessment methodologies are sophisticated. And yet, incidents keep happening because the failure modes are increasingly social, institutional, economic, and political rather than purely technical. The question isn't whether we know how to store ammonium nitrate safely. We've known that since at least 1921. The question is whether the systems we've built to ensure that knowledge gets applied consistently, everywhere, every time, are robust enough to withstand the pressures that constantly push against them. And that question leads us to something that might seem surprising in a story about explosions and toxic clouds. It leads us to the concept of slow violence. It's a term coined by the writer and scholar Rob Nixon in 2011, and it describes a kind of harm that's gradual, dispersed, and often invisible, the opposite of the spectacular, instantaneous catastrophe. An explosion makes the evening news. A slow leak of hexavalent chromium into groundwater over 20 years does not. At least not until someone notices that the cancer rates in a particular zip code are 3 times the national average. And this concept of slow violence is, in many ways, the shadow story that's been running underneath everything we've talked about tonight. Think about it. We started all those hours ago with the visible disasters, Oppau, where a hillside simply vanished in a column of smoke. Texas City in 1947, where a ship turned a harbor into a war zone. Bhopal, where a cloud rolled through sleeping neighborhoods. These are the events that get names and dates and memorial plaques. They're horrifying, and they should be remembered. But for every Bhopal, there are hundreds, maybe thousands, of communities living with chronic, low-level chemical exposure that never reaches the threshold of disaster in any official sense. The contamination is too slow, too diffuse, too entangled with other factors for anyone to point at a single moment and say, "There, that's when it happened." And here's the thing. The regulatory frameworks we've built over the past century and a half are overwhelmingly designed to prevent acute events. The Seveso directives, OSHA's Process Safety Management Standard, the EPA's Risk Management Program, these are all oriented around preventing the big sudden release, the explosion, the toxic cloud, the runaway reaction. And they've gotten reasonably good at that in places where they're actually enforced. The rate of major industrial accidents in countries with mature regulatory systems has genuinely declined over the decades. That's real progress, and it matters. But slow violence operates in the gaps between those frameworks. It lives in the permitted discharge limits that are technically legal, but cumulatively harmful. It lives in the acceptable risk calculations that assume exposures are isolated when, in reality, a community might be dealing with emissions from a refinery, runoff from an agricultural operation, and legacy contamination from a factory that closed 30 years ago, all at the same time. The body doesn't experience these exposures one at a time. It experiences them together, day after day, year after year. And our regulatory system, for the most part, evaluates them one chemical, one facility, one permit at a time. There's a term for this: cumulative impact assessment. And it's something environmental justice advocates have been pushing for decades. The idea is straightforward. Instead of asking whether a single facility's emissions are within legal limits, you ask what the total environmental burden on a community looks like when you add everything together. California actually passed a law in 2022, Senate Bill 1000, building on earlier efforts to require that local governments incorporate environmental justice into their general plans, considering cumulative impacts. It's a start. But it's still the exception rather than the rule, and translating the concept into enforceable regulation is enormously complex. How do you assign responsibility when the harm comes from 20 different sources? How do you set limits that account for interactions between chemicals that have barely been studied in combination? This is where the science gets genuinely humbling. We talked earlier about how the post-war chemical revolution produced tens of thousands of synthetic compounds faster than toxicology could evaluate them. That gap has never fully closed. The EPA's Toxic Substances Control Act, originally passed in 1976, grandfathered in something like 62,000 chemicals that were already on the market, essentially assuming they were safe until proven otherwise. The 2016 update, the Lautenberg Act, improved things by requiring the EPA to actually evaluate chemicals and giving the agency more authority to demand safety data from manufacturers. But the pace of evaluation is still glacial compared to the number of substances in commerce. There are something like 86,000 chemicals registered for use in the United States, and the EPA has completed risk evaluations on a small fraction of them. The European Union's REACH program, which we touched on earlier, takes a more proactive approach by requiring manufacturers to provide safety data before a chemical can be sold. It's arguably the most comprehensive chemical regulation system in the world, but even REACH has struggled with the sheer volume of substances and the complexity of assessing real-world exposure patterns. And then, there are the chemicals we thought we understood, but didn't. PFAS, per- and polyfluoroalkyl substances, are maybe the most striking example right now. These are the so-called forever chemicals, a family of thousands of synthetic compounds that have been used since the late 1940s in everything from non-stick cookware to firefighting foam to waterproof clothing. They're extraordinarily persistent in the environment. They don't break down. They accumulate in water, in soil, in blood, and we've been producing and releasing them for over 70 years. 3M, one of the major manufacturers, actually knew about potential health concerns as early as the 1970s. Internal studies showed that PFOS, one of the most common PFAS compounds, was accumulating in the blood of workers at their production facilities. But that information didn't become widely public for decades. By the time the scope of the contamination became clear, PFAS were essentially everywhere, in the drinking water of hundreds of communities, in the blood of virtually every person tested in industrialized countries. The town of Parkersburg, West Virginia, became one of the most visible examples. DuPont's Washington Works plant had been releasing PFOA, another common PFAS compound, into the Ohio River and local waterways for decades. A farmer named Earl Tennant noticed his cattle were dying in strange ways. Tumors, blackened teeth, organs that looked wrong. He went to a lawyer named Robert Bilott, who spent years piecing together what had happened. The resulting litigation, which stretched over more than 15 years, eventually revealed that DuPont had known about the toxicity of PFOA and had concealed it. A massive epidemiological study, the C8 Science Panel, covering nearly 70,000 people, found probable links between PFOA exposure and kidney cancer, testicular cancer, thyroid disease, high cholesterol, preeclampsia, and ulcerative colitis. DuPont and its spin-off Chemours eventually paid hundreds of millions in settlements. But here's what makes the PFAS story so emblematic of slow violence. There was no explosion, no toxic cloud, no single day you can point to. The harm accumulated invisibly, molecule by molecule, year by year, in the bodies of people who had no idea it was happening. And the regulatory response has been painfully slow. The EPA didn't establish a legally enforceable maximum contaminant level for PFOA and PFOS in drinking water until April 2024, setting it at 4 parts per trillion, which is extraordinarily low and reflects just how toxic these compounds are, even at minute concentrations. 4 parts per trillion. To give you a sense of scale, that's roughly equivalent to 4 drops of water in an Olympic swimming pool. The fact that we're setting limits that low tells you something about how seriously the science now takes these compounds. And PFAS is just one family of chemicals. There are others: microplastics, endocrine disruptors, certain pesticides, where the science is still catching up to the exposure. The pattern is always the same. A substance gets widely adopted because it's useful and profitable. Early warning signs are ignored or suppressed. Decades of exposure accumulate, and eventually the evidence becomes undeniable. By then, the contamination is widespread and the cleanup costs are staggering. It's the Radium Girls story, replayed in slow motion across entire populations. So where does all of this leave us, here at the end of this long, winding journey through the history of chemical disasters? Let me try to pull some threads together gently, because I think there's actually something hopeful buried in all of this, even though the story is often grim. The first thing worth recognizing is that we have learned, genuinely, substantially learned. The Oppau explosion in 1921 happened in part because no one fully understood how ammonium sulfate nitrate could detonate under certain conditions. Today, the chemistry of energetic materials is deeply understood. The Bhopal disaster happened in part because there was no legal requirement for companies to tell surrounding communities what chemicals they were storing. Today, right-to-know laws exist in most industrialized countries. Piper Alpha happened in part because offshore safety was governed by prescriptive checklists that couldn't adapt to novel risks. Today, goal-setting safety case regimes require operators to demonstrate that they've identified and mitigated risks specific to their operations. Each disaster taught something, and those lessons were, eventually imperfectly, encoded into regulations, standards, and engineering practices. The second thing worth recognizing is the pattern we keep seeing. The lesson gets learned, the regulation gets passed, and then time passes, and the memory fades, and the pressure to cut costs or streamline oversight builds, and the protections erode, tighten and relax. We saw it after Tianjin. We saw it after Texas City. We're watching it happen right now with the Railway Safety Act stalling after East Palestine. This cycle isn't a mystery. It's a predictable consequence of how human institutions work. Urgency fades, attention shifts, and the forces that benefit from less regulation are persistent and well-funded, while the forces that benefit from more regulation are diffuse and episodic. Understanding this cycle doesn't make it less frustrating, but it does suggest that the solution isn't just better regulations. It's building institutions that are resilient to the inevitable pressure to weaken them over time. And the third thing, and this is maybe the most important, is that the nature of chemical risk is shifting. The acute disasters haven't gone away, as East Palestine and Tianjin remind us, but increasingly, the biggest chemical safety challenges are chronic, cumulative, and systemic. They're about the slow accumulation of PFAS in drinking water. They're about the combined impact of multiple pollution sources on communities that are already overburdened. They're about climate change interacting with chemical infrastructure in ways we're only beginning to understand. Floods inundating storage facilities, wildfires burning through contaminated land and lofting toxins into the air, rising temperatures accelerating the degradation of aging equipment. Hurricane Harvey in 2017 flooded chemical plants and Superfund sites across the Houston area, releasing who knows what into floodwaters that then flowed through neighborhoods. That's not a traditional chemical disaster. It's a climate disaster and a chemical disaster fused together, and our regulatory systems aren't really built for that intersection. But you know what gives me some hope? It's the people. It's always been the people. Alice Hamilton, walking into factories in 1910 to document lead poisoning when no one else would. The Radium Girls, refusing to be silent about what was happening to their bodies. The residents of Love Canal, organizing and demanding answers until the government had to listen. Robert Bilott, spending decades of his legal career fighting DuPont over PFAS. The firefighters in Tianjin, who ran toward a disaster they didn't have enough information to understand. The people of East Palestine, demanding accountability and transparency. Throughout this entire history, the advances in chemical safety have almost never come from the top down, at least not initially. They've come from individuals and communities who refused to accept that their suffering was just the cost of doing business. And that, in a quiet way, is the most important engineering lesson of all. The chemistry matters. The process design matters. The containment systems and the pressure relief valves and the safety instrumented systems, all of it matters enormously. But none of it works without the human systems that surround it. The willingness to report a near miss, the culture that treats safety as a value rather than a cost, the regulatory agency that has the funding and the independence to actually enforce the rules, the community that has access to information about what's being stored next door, the political will to maintain protections even when the memory of the last disaster has faded. We know how to make chemicals safely. We've known for a long time. The question has always been whether we choose to, consistently, even when it's expensive, even when it's inconvenient, even when no one's watching. And that question doesn't have a final answer. It gets asked again every day, in every plant, every boardroom, every regulatory office, every community. So as you lie there, maybe drifting off, maybe already half asleep, let that settle. The story of chemical disasters is, at its heart, a story about what we owe each other. The workers, the neighbors, the communities downstream and downwind. It's a story about the distance between what we know and what we do. And it's an ongoing story, one that's being written right now, in decisions large and small, by people whose names we'll never know. Some of those decisions will prevent disasters that will never make the news precisely because they were prevented. And that's the strange, quiet heroism of good engineering and good governance. When it works, nothing happens. The plant runs safely. The water stays clean. The community sleeps soundly. And no one has to learn the name of the town the hard way. That's the goal. That's always been the goal. And it's worth holding on to gently as you drift off to sleep.